and I will screen share. So hopefully, if somebody got a thumbs up, we're good to go. Okay, so thank you for joining us. So I guess most people on this call have an interest in indoor air quality. And what we wanted to do in this session was to really kind of give you some further details and information and just tell you a bit about our experiences and the materials we developed so you can have access to them, and opportunities to also do some indoor air quality monitoring yourself if you don't have direct access to the equipment at the moment. So we've got you for an hour and a half. We plan to cover 3 themes. So I'll give you an overview of the Home Biome project, which was a NERC funded project that the indoor air quality monitoring was part of. But we are just going to focus on the indoor air quality element of it and interdispersed or talking about that with the resources and opportunities for you to get involved and really do your own projects as well. So citizen science is a potentially powerful approach for indoor environmental monitoring, particularly of the residential environment. Citizens from around the world send in house dust samples, and we monitor the trace element content in their vacuum dust. And this has been linked to the international house dust study called DustSafe. As part of the Home Biome programme, we're also doing more around the microbial environments in our indoor environment and looking at antimicrobial resistant genes in our indoor vacuum dust. But today's session, we're going to report on indoor air quality, and we're very much going to have a northeast focus, partly driven by the fact that for the 2 years of this project, we were largely in and out of lockdown. And what we want to cover today is an insight into some of the PM 2.5 concentrations we found, and talk you through some of the ways we've started to look at exposure estimations. So why should we care about indoor air quality? Well, we typically spend 80% plus of our time indoors, and it's estimated that 4.2 million premature deaths globally are due to poor indoor air quality, or indoor air quality and poor outdoor air quality. So majority of these deaths are associated with fine particulate matter. So particulate matter is principally ingested via dust that stick to our hands or stick to things that particularly children may be putting in their mouths. It's also via inhalation. And once we're exposed, this can initiate or enhance disease in humans. So some of the main sources of indoor air pollutants I've pictured here. So we've got burning of solid fuels indoors, we've got candles, incense, smoking, cooking, and the ingress of outdoor poor air quality indoors is a particular issue, especially in busy urban areas or near busy roads. So because we're focusing on the indoor air quality element today, let me just run through the kind of the 3 key research questions we were asking. So the first one, what are the typical concentrations of respirable particulate matter to which we are exposed in regular UK homes? The second one, what are the common activities that generate elevated levels of respirable particulate matter? How elevated are these spikes? How long do they last? And can we detect these in other rooms in the house? And the third one was really, can we use a citizen science approach to help us estimate the typical range of inhalable particulate matter in our homes, and also the trace elements in airborne and settled particulates in UK homes? So we approached this, the air quality element, as follows. We gave our participants 2 Aeroqual 500 particulate monitors to use to measure PM 2.5 in their kitchens and their living rooms. You can have on the size of the card, the memory, 1 week of measurements at every 3-minute intervals. And the participants recorded an activity diary for us. They also gave us a vacuum dust sample, and they completed a questionnaire. So part of this session is about sharing these materials with you. So what I'll do now is I'll pass to my colleague Lindsay to tell you more about these materials, how we develop them and where they're available. So Lindsay, over to you.
Hello, I'm going to introduce you to the equipment and resources we use for our study and which are now available for you to use. We have Aeroqual Series 500 portable air quality monitors, which I'll show you in a moment. And we also have a toolkit of help sheets, manuals, checklists and example analyses, questionnaires, reports and code, which I'll come to later. So I'm going to, Jane, if you could stop sharing, please. Great, and I'm going to show you some of our kit. So if you borrow it, it will come in a box like this. I'll just open it up. And you'll get a base unit. And a charger. And a download cable and some sensors. So this is a inhalable particulate sensor. It measures PM 2.5 and 10. And another one we will give you is CO2 and VOC, and these are chemical sensors and they look like that. The Aeroquals use a laser particle counter technology to measure the particles. So that gives a calculated mass concentration based on assumed density and shape. And the VOC and CO2, as I said, are chemical sensors. We have one of these sets in Nigeria and two in the UK, and you can borrow them for a couple of weeks at a time. They'll be available till at least the end of August and hopefully until the end of the year. Get in touch with Jane or I if you're interested in using them. We will post them out to you, but you need to cover the costs of sending them back to us. And in the UK, that is about £6.50 signed delivery, so it shouldn't break the bank. Coming back. Right, I'm going to share screen now, hopefully. How's that looking? Great. Oh, so that's the kit, and this is the toolkit that we have provided for you as well. So it contains example documents of everything you need to get started with a citizen science indoor air quality study, and specific help sheets for using the monitors that we have for loan. This includes a checklist for working with participants in citizen science, the long form user guide manual for the Aeroqual sensors, and then a short cheat sheet just to get you up and running so you can use them quickly. And then we have participant information for a citizen science study, and an example consent form, and then a short survey on things that can impact indoor air quality, and a time activity diary, some examples of analysis you could do with the data, and an example of a report you could give back to your participants. And all of that info is available via Map My Environment on the Home Biome page, and so you can get to it using this address here. I think the most important, or maybe the most useful document when you first get hold of the monitors, is the Aeroqual setup cheat sheet. And it's got brief instructions for setting up and downloading data, as well as the link to the software you'll need to be able to download the data. You need to register for this software, but it's free. And when you download the data and export it, it will look like this. The PM data here is in milligrams per meters cubed, So you need to multiply it by 1,000 to convert it to the standard micrograms per meter cube that are usually used. Okay. So a little bit about quality control. Air quality monitors use a range of different technologies, and the measurements that they take range in accuracy. There are some relatively cheap monitors available, which might be fine to use if you just want to know if your carbon dioxide or your particulate concentrations are increasing or decreasing with different activities. Just to say that the sensors we have available for loan have been factory calibrated, but maybe you want to carry out some independent checks, or you have access to other air quality monitoring equipment that you'd like to assess. It's just a good idea to have an idea. It's just, yeah, you need to have an idea of how you might carry out some basic quality control checks on your data. And I'm going to look in a bit more detail at 3 checks that we undertook. The first one was inter-unit precision, and then we looked at accuracy by comparing our sensors with more accurate technology, and then we used the gold standard, which is a mass deposition comparison, or comparison with, or also known as gravimetric analysis. Okay, let's go. So a bit of inter-unit precision here. This picture is a co-location study that we undertook to see how various air quality monitors that we have compare with each other. You'll recognise the Aeroqual 500s there with the laser particle counter technology. This is also known as photometers or nephlometers. So you might hear those terms. That's what it means, laser particle counter. And the ones in the background are particle plus monitors, and these are particle counters. They collect every particle by size and then put it in a bin, depending on the size, and then they estimate the mass of each bin. And this is accepted as a more accurate technology. The first test we did was to see how well our Aeroquals that we're using for the study Jane's talking about, how do they compare with each other? And that's what you can see in this table. You can see that all the correlation coefficients, we've used Pearson's R here, they're all 0.9 or over, so that's pretty good. We're happy with that. The next quality control test that we did was looking at how the Aeroquals compared with the Particles Plus, a more accurate monitor. And I need to thank Kamal Maji for doing the data wrangling for this and creating these lovely charts. By adding a line of best fit to the charts, we get the R squared, the slope, and the mean offset difference. So that's the intercept. And I'll just and this is what they look like. So correlation, this time R squared, still acceptable. The scaling factor for most of these is fine. It's 0.1 to 1.1, 0.8 to 1.1. It's acceptable, but you can see that PM7 has the scaling factor of 1.5. So that means that you'd have to multiply the Aeroqual value by 1.5 to give the equivalent value that you'd get from the more accurate sensor. And this isn't acceptable to us, so we won't be using that sensor anymore. And you can use the scaling factor and the intercept in the equation y equals a plus bx to convert your Aeroqual or whatever sensor you're testing against your reference, to convert it to a reference monitor value if you need to. Okay, so for the next slide, I'm hoping to hand over to Sonia to talk about the gravimetric analysis. Have you got a signal at the moment? Are you there?
I do have some signal with an enormous electric storm going on. at the moment. Wow. So I hope that everybody can still hear me though. So what we've done next is to look at the gold standard, which I'm sorry, this is a bit weird for you guys. An electric storm in the UK is not really something that happens a lot, is it? But anyway, so what we did look at was the gold standard using the gravimetric method. So we've had some filters that actually was weighed beforehand, and then it was connected to a PM2.5 impactor or a sampling head, which would then be connected to a little pump. The pump would go at a standard rate of 2 liters per minute, and that is then calibrated beforehand and during the measurement. And so we are fairly confident that we are delivering a constant volume of air through our filter. We collect the particles and then we weigh it afterwards again. So if you could just forward the slide to the next one. So the first thing that we're going to show you, I think, is the PM2.5, if you can. Yeah, so that is the PM2.5. And that was measured by a continuous monitor. AS stands for air sensor. So it's got a slightly different particle counter than the Aeroqual. Although it is manufactured by the same company, it has been done by a different third party. And so we see a typical ratio of a higher PM10 value indoors than what we have observed for the PM2.5. And as one would typically see, sorry, as what one would typically see is a variation in the PM2.5 and PM10 concentrations. It's specifically interesting to see that the PM2.5 varies a lot more than the PM10, and that the PM10 stays fairly constant. So that was the continuous monitor over 7 days. That is the period through which we have analyzed it. And then we continue on to the Aeroqual. And we first start with the PM2.5, and you can see that there is a very good correlation between the two continuous monitor sensors. And from then on, the PM10, which you can also see, the PM10 is absolutely spot on. As a matter of fact, the R-square value for that is 1. So they are perfectly in sync in terms of their particle mass concentration that they've estimated. Then we see the gravimetric result, which was 5.06 micrograms per cubic meter of air. So that was the average over the 7 days. The next one would be the air sensor average, which was 4.49, and the one after that would be the Aeroqual one, which is 4.42. So we do see that there is a very good correlation in terms of the so-called gold standard and our PM2.5 that we have observed. And that gave us some confidence in the continuous monitors. And I think that is all I needed to say.
Thank you very much, Sonia. That's great. Okay, so now you know how to use your monitor and how to carry out some quality control to judge the accuracy of your equipment. You might want to recruit some more people to take part in your air quality research. And to help with this, we have included the citizen science resources that we developed in the toolkit that's available to you by this link again. So the participant information includes, sorry, I'm just moving on. Oh dear. Ah, yes, participant information. So that tells people who are thinking of that you invite to take part. It explains to them why you're doing the study, what they will be asked to do, who can take part, who can't, what if there's a problem, who to contact. And we've highlighted the parts of the document that you absolutely need to change. And you're free to edit the rest too, but this is just a starting point for you. And the same goes for the participant consent form. So these two documents clearly state what the participant will be asked to do and what the research team will do to keep the participants' information safe and confidential, and also includes tick boxes for things like whether the participant would like to know their own results. If you're doing citizen science, you will probably need to get ethical approval from your institute before undertaking any work. And these two documents and any other documents that participants will see will need to be included in your application. This is another document they'll need, and this is a 10-minute survey we developed. Again, it's a bit of a work in progress because we change everything as we get feedback. But the survey covers all sorts of things that might influence air quality in a home, like the number and age of household occupants, whether they have pets, covers behaviours like burning incense or candles, home construction materials, home heating and cooking fuels, ventilation and extractors, even cleaning habits. Another document for the participants is the activity diary. And it's most valuable for interpreting what the homeowner is going to. So when you've got the data from the homeowner, then you can match activities listed in this activity diary with peaks in the data. So you could include tick boxes for open windows, doors, or extractor fans, and you might be able to identify the impact these have on air pollutant levels during polluting activities. This diary is, again, a work in progress. It's very much a balance between what you want and what's practical for the participants to complete. We had feedback to say that more tick boxes would be helpful, help participants know what they should be including in there. It would encourage children to get involved in the diary keeping. But remember, you only want to ask for information that you will use. It's a waste of your participants' time, and so that makes it unethical to ask for more than you will need. Okay. So this brings us nicely to an opportunity for any questions you might have. Have we got anything in the chat? Or does anyone want to raise a hand?
So please feel free to put your hand up and ask your question yourself as well. We will carry on with the presentation, so there will be other opportunities. But if anyone wants to ask anything at this point, you're very welcome to, while Lindsay and I are switching over presentations. Okay, shall I carry on at this point then? Lindsay, can I just double check you can see the screen? I've managed to switch it over.
Yes.
Cool. Okay. So that hopefully gives you, hopefully I can get this up and running, gives you an update of getting going. So let me come back to our research questions and share with you some of our initial results and findings. So we asked, what are the typical concentrations of respirable PM to which we are exposed in regular homes? So it was very much a UK Northeast focused. We've done it during the 2 years of the pandemic. And what common activities were generating these spikes? How long did they last? And could you detect one activity in a different room in the house? So what I have here is a box and whisker plot summarizing the PM 2.5 concentrations on the y-axis, and each of the homes, the 18 homes in our study, along the x-axis. The kitchens are in orange, the living rooms are in blue. So what are the key points to note? First of all, the PM 2.5 concentrations were similar in kitchens and living rooms within each home. If we put all the data together for the kitchens, there was an average concentration of 16 micrograms per meter cubed in the living rooms, and 20 microgram per metre cubed in the kitchens. What stands out for us was homes 5 and 6, as you can see here. Both of those homes had homes with smokers. And in the main, the smokers didn't smoke anywhere near the monitors. They were smoking for home 6 in a conservatory adjacent to the monitors, but you could still see elevated PM concentrations within the indoor environment in the kitchen and the living room. Home 13, that we have here, was an interesting one. They had a number of cooking accidents, very well timed for us while they were doing their air quality monitoring in the kitchen, burnt toast and 1 or 2 other activities. And you could see that again through a raised average over the course of the week we were monitoring. So now there are no domestic indoor air quality limits or standards, but the EU has a legal limit for outdoor PM 2.5, and the annual average is 25 microgram per metre cubed. So it gives you a sense of what the indoor environment is compared to this 25 microgram per metre cubed. So the home with one of the smokers had a mean for their week of monitoring, a mean concentration of 95 microgram per metre cubed, whereas the non-smoking, more, I guess, typical household in our survey had a mean PM 2.5 concentration of 14 micrograms per metre cubed, compared to this 25 microgram per metre cubed annual average limit. So let's look in more detail at 2 of the home diaries. So we'll look at home 6 and we'll look at home 8. So home 6, single occupancy, smoking household. So the annotated chart shows the concentrations again of PM 2.5 on the y-axis, and the x-axis has the days of the week that we were monitoring over. We can see peaks getting up to about 600 microgram per metre cubed, and almost all of the peaks in this household were linked to cigarette smoking in a conservatory attached to the house. So peaks 1, 2, 3, 5 and 7. And the mean, as I've already mentioned, for the smoking household was 95 microgram per metre cubed. So let's look at home 8, a family of 3, a non-smoking household. Same layout, PM on the y-axis, days of the week on the x-axis. And what we see is fairly typical in our households. You see regular peaks associated really with lunch and dinner. So peaks 1, 3 and 4 here are associated with frying and baking activities. And we see peaks getting up to about 400 microgram per metre cubed, with an average over the week of 14 microgram per metre cubed. So that kind of gives you a kind of sense of scale of what we were monitoring on the indoor environment. But our other question was, do we see what's going on in one room in an adjacent room in the house? Yes, we do. So here we have overlaid concurrent PM concentrations in the kitchen in orange and the living room in blue over the course of the week. And we can see strong similarities in the timing of peak concentrations between the 2 rooms. Kitchens generally, though not always, in our study had higher maximums than the living rooms, but the living rooms tended to have slightly higher background concentrations of particulate matter. And we wonder whether this is because potentially the kitchens are slightly better ventilated, or people use ventilation whilst they're cooking, so that the background level drops quicker in the kitchen. But again, we haven't fully explored all the reasons for our findings at this point. So I'm going to pass back to Lindsay, because clearly we've generated a lot of data and I've just given you some of the kind of overview and some of the highlights of what we've found. But I'm going to pass back to Lindsay now to tell you a little bit more about how we feed back to participants. Thanks, Lindsay.
So everyone can hear me and see the slides now. Great. Yeah, so you've got all this complex information. How are you going to get it back to your participants? You need to presume that they don't know anything about air quality, but they're interested to know more. they'll want to know how their air quality compares with other people in the study and how they can improve their home air quality if they want to. They'll need a certain amount of background information, such as how to read any charts you include and what the units mean. People don't generally want lots of reading, so minimise the text and use pictures where possible. Your report will probably have mostly generic information with some participant-specific information that's quick and easy to generate and insert. Smashing. So this is some excerpts from our report, which is included in your toolkit. And we've included a description of particulate matter, how it's measured, the units, and how to interpret the results. And we've used this bespoke line chart for comparison with other homes in the study. Line charts are recommended for risk communication with the general public, as they're easier for non-scientists to understand than more complex charts or tables. We also include outdoor air quality and particulate matter regulatory limits for comparison. Excuse me. Because there aren't any indoor air quality limits to compare with. We've got bespoke, there's this chart here, which is similar to the ones that Jane was showing you. So we put one of those into the report as well. And that's showing the individuals or that participant's home, and we've labelled the top 10 peaks of their particulate producing activities. The central element of this study is around environmental awareness raising, and so the feedback report to our participants is really important. And at the end, we include tips for reducing exposure to inhalable particulates in the home. That's these bits here. Having a spot of bother changing my slides. Just come out.
It obviously wants to stay on the participant feedback one. Way, you moved it on.
Right. In order to create those charts that you saw in the report, the line chart we included is generated by Aeroqual, written by the Apperception Group, who also run the Map My Environment website that hosts the home biome web pages and the indoor air quality toolkit. So they've kindly made the R code available to you via this GitHub link here. Down here, can you see my arrow? Where's it gone? Oh dear me. Well, highlighted in yellow at the bottom of the slide is the link to the R code. And that R code is also available, or you can link to it next through the study data download and analysis document that we have in the toolkit. And this has general how to do all the charts that we include in the report, to download the data, anything that we've done is explained how to do it there. So and what's important at the bottom is we'd love to see the reports that you make, and so please do send us copies of it. We're very interested to see where this goes. And that takes us back to some more questions, if there are any.
So yeah, please, again, if you have any questions or queries around some of the activities that we've been doing, some of the materials that we've made available, especially as Lindsay's obviously dying of her cold, bless her. I'll give it a moment. If there aren't any questions, I'll just carry on with the last block. Mukata, I see you've got your hand up. Would like to ask your question live, or you can turn your microphone on.
Hi.
Hi, we can hear you.
All right. Thank you for today's program. It's been educating so far. My question is as regards taking the air sampling itself. Do you, at the point when you turn on the handheld, okay, I happen to have one, to borrow one from Lindsay. When you turn it on, there's a 3-minute period where it has to set up. Now, when it's ready to take readings, when you start taking those readings, let's say for the living room, for example, the moment you want to switch to the kitchen to take the readings of the kitchen, do you switch it off, or you just move to the kitchen and it just readjusts itself? And if you actually need to switch it off and turn it on, in a situation where, in my own case, I have to take readings at a faster pace, and I think it will be difficult for me to be turning it on at every point in time, waiting for 3 minutes and then going back. And during that period where you switch from the living room to the kitchen, there seems to be some spike, or let's say, yeah, some spike in numbers. You're not sure at what point would you say this value is, the value showing is accurate. Is there like a way to know? Because I noticed there were some symbols on the screen. I could see some triangle symbols. I'm not sure, maybe I'm way too forward. Maybe this thing will still be discussed later on. So those are my series of questions. Thank you.
Thanks, Mukhtar. So this is about the actual devices that we're loaning out. So sounds like Mukhtar's already got one of the devices. Lindsay, I don't know if you want to comment first about the actual switching it on and off, but I would just add a clarification that we're only sending out one device so it can go to more people. But obviously when we had the citizen scientists involved, they had one that was permanently based in the kitchen and one that was permanently based in the lounge. So there are multiple devices that we would put in a house that would run simultaneously when we did the project. But I'll pass to Lindsay to comment about the case of switching it on and off when you move around.
Yes, I would not switch them off whilst moving them around, but I would take a note of the time that you're in one room and the time that you get to the next room. They're supposed to be good from when they're first, after they've warmed up. They should be ready. They should be pretty reliable from the get-go, but you could wait 5 minutes from switching them on if you wanted, if you found you were getting a peak. I can't say I noticed that.
I mean, the peak may be about you disturbing dust, or you actually are moving particles around by moving, or putting it down on a different surface. So be aware of that too, as I'm sure you are. So does that answer your question sufficiently, Mukhtar?
Yes,
for the moment.
That answered my questions for the moment. But how about the symbols on the screen that I mentioned? There seem to be a triangle symbol showing, and then a sort of inverted Bluetooth sign. I'm not sure it's Bluetooth, but I just call it Bluetooth sign. And I've checked YouTube and all. I don't think I've seen anything to explain that. Thank you.
Okay, well, all that information is in the manual. But I can tell you the triangle shows how much data you've got stored in there, and the cross signal shows whether you've got it. It's to do with charge. I think it says it's got that on if it's plugged in.
Okay, thanks, Lynn. So we're happy to come back to I say at the end, Mukhtar, since you've already got a unit, if you want to come back and we can maybe triage any further questions at the end of the formal presentation. But again, if people are thinking of borrowing them, it's good to hear everyone else's experiences, because I'm sure you'll probably ask the same questions too when you get hold of it. Shall I just go to the questions in the chat before we move on to the final block? So Gina asked, sorry, there's somebody else got the hand up. I was about to read Gina's question out. Okay, Gina asked, how much do the devices cost and can they monitor outside as well as indoor PM? And do the devices display the actual value on the monitor? I would say I will guess at the cost, but I know Lindsay will probably remember better than me because we just bought some new units a couple of weeks ago. Can you remember the cost of the Aeroqual? The unit's separate to the head.
In the unit, it's about £2,000, and the possibly. Can I check that and I can get back to everyone with that information? But the sensors you buy independently as well, and I think they're up to £500 each.
Lindsay, there was also another question from someone about the smokers, whether they were instructed to smoke in a different room.
It again. When do you have it?
No, they weren't, but I did ask a couple of smoking households to take part, just to see what difference it made. Yeah.
I think that's a good point, because whether or not, it depends what you're monitoring with your indoor air quality. So you may or may not want smokers to take part. And if you've got smokers taking part, you may want them to smoke outside. So again, it depends on the aims of your indoor air quality study. Ours wasn't specific in terms of, were we looking at somebody sealing up part of their house because they had some new retrofit, and we were looking at the impact on indoor air quality. So we didn't want smokers to influence the indoor environment. So this was more of a general one to get a sense of what real people were being exposed to in real indoor environments. But you'd need to think a little bit more about whether or not you want smokers involved and your advice to smokers, because it clearly does have a big impact on the mean concentration of PM you monitor over the course of the study week. Okay,
and
thanks.
I forgot to say, yes, you can read on the front screen the values of what you're measuring.
And this was one of the reasons why we plumped for the Aeroquals, because they are a really simple device where the participant can keep an eye on the display. So it wasn't linking to the internet. It didn't require on an internet activity or download, and participants can see the screen themselves, and they can monitor it themselves, how it changes over the course of activities. So part of the reason we selected the Aeroqual in the first place.
And they can be used indoors and out, but they're not waterproof. So you could take them out on a dry day. Yeah. But you couldn't leave them outside. Certainly not in the UK.
So if you do borrow one, we are targeting indoor air quality studies. But yeah, as Lindsay says, please feel free to walk outside with it as long as it's not raining. Okay, we'll come back to additional questions. We'll do a few more slides. Okay, thank you. I'm going to see if I can share my screen again now. Okay. Just wake it up. So going back to our research questions, we wanted to know, can we use citizen science approach to help us estimate the typical range of inhalable PM 2.5 and trace elements in airborne and settled particulates in UK homes? So we think about what we've now told you, the data we've collected and the information we've got. So we have the average PM concentration in participating homes air. We've also got their vacuum dust and their ED-XRF analyses that we undertook on their vacuum dust. So we've got the two elements, so we can estimate the concentration of trace elements in indoor air particulate matter. I should say these estimates are clearly estimates, because there obviously are a range of caveats with many of these calculations about going from these two parameters to estimate indoor air trace elements in indoor air. So we need to assume that the trace element concentration in the vacuum dust is equivalent to that in the PM 2.5 fraction of the air. And we also note a caveat that the greatest peaks in particulate matter generally occur with cutting activities, and the predominant particulate matters released during cooking are unlikely to be dominated by trace elements. So it probably is a mix. I don't know, it could be a worst case scenario, but one of these may combat each other. So there are a range of caveats. These are estimates, but let me go through some of the estimates we've got and why we actually feel we have some confidence in them. So first of all, the first element, the XRF analyses of the vacuum dust. So here I just show you in a simple box plot the elements we were interested in along the y-axis and the trace element concentration as we determined on little pellets of vacuum dust. You can see that zinc has some of the highest concentrations, and just picking lead because many of us work with lead in an indoor context from different sources and backtracking of dusts. So lead concentrations mostly range from 50 to 700 milligrams per kilogram in our 18 homes that we were studying. So we also had the PM 2.5 concentrations. We multiplied the two together and it gives us this caveat full but estimated range of trace element concentrations in PM in indoor air in nanograms per meter cubed. So along the bottom again are the elements. On the y-axis we've got the trace element concentration that we've estimated in nanograms per meter cubed. The highest concentrations and the broadest range were for manganese. And just because I'm picking up lead, lead concentrations that we estimated in the trace element concentration in our indoor air range between just below 1 to 12.4 nanogram per meter cubed. What we've also done on the adjacent table is give you the guidelines for trace elements in air where we've been able to source them. So whether they're the WHO, ATSDR from the US or the European Commission. And all our homes actually were below these trace element concentration limits or guidelines. But let me tell you a little bit about it, why in more detail to explain why we have some confidence in these estimations despite all of these caveats. So along the top row in dark green is our data. What we do have is an outdoor study in Newcastle on outdoor PM in Newcastle air collected on filter papers with a high volume sampler, and the filter papers were then analysed direct themselves. And there's a reasonable consistency between our indoor air estimations and these real sampled on filters outdoor air data for Newcastle. I'll just again draw your attention to lead. So our estimations for lead was 3.6 nanogram per meter cubed. The previous study on outdoor Newcastle air was 12.2, and from the data we've collected through the literature across the UK, then lead concentrations in the UK in air, this is outdoor air, typically is less than 10 nanogram per meter cubed, and it's remained largely steady over the last decade. So what we're now doing is collating data for trace elements in indoor inhalable PM. So actually a plea to anybody out there, if you've got some really good, your hands on some really good published studies of indoor trace element data, then please in indoor air, please send it to us because we're just embarking on that at the moment. And all I've put here are some examples of outdoor air trace element concentration that we've collated so far. Okay, and I think that's me. I'm going to pass back to Lindsay now to finish off the last few slides, and then we'll open the floor again to questions. Thank you.
Okay, can you see my slides and hear me? Great. So this is what we're working on now. Well, I have to say, with the help of Kamal Maji, again, my wonderful colleague here at Northumbria, who's listening. Anyway, yeah, so we're looking at respiratory dose estimations. And we're doing these for children and adults. So at 3 months age, 8 years, 21 years, and 65 years old. And we're looking at their head and airway, tracheobronchial and pulmonary alveoli deposition. And this illustration shows the different deposition zones. And then once we've got these deposition values, we're going to estimate carcinogenic health impact from them. But we're just working on that now. So hopefully, we will be able to report that soon. So just to summarize what we've found to date, I'll go through the questions again and then I can give you the answers. So what are the typical concentrations of PM2.5 to which we're exposed in UK homes? And we found a range of from less than 1 to nearly 1400 micrograms per meter cubed PM2.5 with an average of 18 and a 95th percentile of just about 300 micrograms per meter cubed. So on average, the PM2.5 mass fraction was about 60% of the PM10 concentration. Although you get more PM2.5, you get a higher fraction in homes of smokers. So cigarette smoke has a higher proportion of PM2.5. Next question, what common activities generate elevated levels of particulate matter and can we detect these in rooms in the home? Yes, absolutely. The cooking dominates PM release unless the home has smokers. And you can see this impact in other rooms in the house as well as where the activity is happening. Last question, can we use citizen science approach to help us estimate the typical range of inhalable, whoops, doesn't move when I want it to, and then it has a life of its own. To help us estimate the typical range of inhalable particles and trace elements in airborne particulates in the UK. Yes, our estimated exposure to trace elements in particulate matter correspond to direct detections made on PM collected on filter papers and also well within what few regulatory guidance and limits are available. If you have been interested in what we've been talking about, you might be interested in these papers. So we have some international analysis of sources and a human health risk associated with trace metals in residential indoor dust. And another one on bacterial diversity in domestic dust. Watch out for a paper coming soon on the data that Jane's been talking about today on our indoor air quality study. And then that just leaves us to say thank you very much for joining us today. If you're interested in borrowing the kit, contact Jane or myself, and those are our email addresses there. And just to thank all the collaborators that made this work possible. Thank you very much. If you've got any questions, any last burning questions, fire away now, please.
So thanks, Lindsay. So yeah, we've obviously got time now for any other questions and answers. If you want to post them in the chat, please do. And obviously you've got Lindsay and I now for up to the next half hour. If you want to ask any other questions, queries, want to borrow the equipment, we've spiked your interest in having a go at indoor air quality and linking it to vacuum dust or whatever, then please just ask your questions or pop things in chat. So we're here for the next half hour.
Jane, there is a question from Will about the XRF analysis in the chat.
Okay, so yeah.
Yeah, asking whether the other elements were also detected.
No, we focused just on the range of, I guess, potentially harmful elements in the dust, because part of this was about feeding back to participants what harmful contaminants may be in their indoor ambient environment. We haven't extracted out the full suite of elements that you can do with XRF. We've only extracted and calibrated those, I think, 6 or 7 key trace elements. But clearly it's another open area for research if you want to obviously borrow the kit and expand and do a range of other elements beyond the ones that we've looked for. I should say at the moment there is 1 kit out in Nigeria. I should have circulated the contact details of the person who's got them, who's got the kit at the moment out in Nigeria. So he would be you can contact him through me if you want to borrow it and you're already out in Africa, because that then saves UK Africa postage issues. So that one will be located out in Africa for the foreseeable future for anybody who want to trial it and play with it and have a go at it. And we have 2 kits that are being loaned out at the moment in the UK. But it'd be wonderful if you did use any of the resources and got interested in indoor air quality, just drop us an email and let us know. We're happy to provide any additional comments or thoughts, and particularly see your reports. We are interested to look at the range of indoor air quality that people are monitoring. So I think someone's kind of, please, can we have the equipment in Nigeria? Yes, what I will do is I will go and I will do it now while maybe Lindsay and Sanya are chatting. I'll just double check the email address of the colleague who's got the kit already in Nigeria. So I'll just pop off and do that, and I'll post his email contact details in the chat.
Ariadne, I'm very pleased that your class wants to use the device too.
Hi, so I've just posted in the chat Abimbola's email address. I think he's using the kit at the moment, but it will remain with him for the foreseeable future, so it can be loaned out to others in Africa. And I say he's based in Nigeria, and we made the most of him having a visit to the UK, where we handed over the kit to make life simpler than trying to post it. So there is a setup out there. It comes with a PM10 2.5 head, CO2 monitor, and I think there's a VOC monitor too with it, Lindsay?
Yes.
None of which we've talked about today. We've focused just on PM 2.5. Okay, I should say if anybody outside the UK wants to borrow it and you're in Europe, we're more than happy to have a go at posting a couple out when we've got them. So if our collaborators in Greece wanted a go at playing with the air quality monitors, you're more than welcome to. Okay, I think that's it. So I'm going to stop the recording.